you very much. Thank you, Ashton. I should add that I actually was on record saying I didn't believe in virtualization. So it's broader than just not believing in containers. And I've got to say, in 2010, when I made that statement, I wasn't even aware of containers. So this is how far the journey has come. So a bit about me. As you suppose, starting at the bottom, I'm still technically a kernel developer. So the subsystems that I'm still listed as a maintainer of are SCSI and PRISC. As you know, as you rise in the ranks at IBM and become the executive distinguished engineer, you're not supposed to touch anything as dirty as code. So technically I do this, which leaves me to be a bit of an anomaly, but not in those two subsystems. So I rarely actually write code for SCSI or PRISC. Mostly I just do patch approval now. And I have a guy in SCSI called Martin Peterson who does all the hard work for me. In fact, all of the work full stop for me. My job basically for SCSI is to send the top pull request to Linus and take the flak if he's in a bad mood. That's all I do. And for PRISC, I don't even do that. I just advise occasionally if there's something going wrong with the memory primitives or something like that. And obviously containers I have actually made quite a large contribution to. And in fact, I'm also working in the field of containers and security, so there's something missing there, which is TPM. I've actually done a lot of work in the Linux TPM subsystem, where I actually wrote the code, which is as a distinguished engineer, which is something I'm not supposed to talk about for IBM. But the reason I got into Parallels in 2011 is as an open source advocate. They just had something they couldn't get upstream, and it turned out to be containers technology that they wanted to get upstream, and they needed somebody who had spent a lot of his career trying to explain in business terms why open source is a good thing, which is why they came to me and persuaded me to get on board with them. And it wasn't until much later when I was actually just, as you do as an engineer, digging around the principles, sort of wondering what they were doing and finding out, this container stuff is actually quite interesting after all. Perhaps I will declare that there is a form of virtualization that I can actually be reasonably comfortable with. The other thing I should say about this talk is that contrary to a lot of the talks here, this will actually be very high level and abstract. So by training, I'm a physicist, which means I tend to think in abstractions first and in details later. The rule in physics is if you get the abstractions right, the details always follow. It's not actually a correct rule, but it's sort of the belief system that we have as physicists. So I use this to guide a lot of what we do at IBM in containers research. So there's a lot of my abstract thought that's not in this presentation that we are actually doing research into in IBM. If you want to actually hear about that, you'll have to come to my talk tomorrow at the Technion. So this is about the abstractions that I've been thinking about that I couldn't persuade anybody at IBM actually to pay attention to, probably because the research is too difficult and too long term. So the reason I'm telling you is because as students, as people who are studying the field, you have much more time and energy than I have to actually go and look at that. But the foundations of this talk are we actually discuss a lot in computing today concepts that we don't actually fully understand from an abstractions point of view. So part of what I'll be doing in this talk is trying to broaden your minds a bit about what terms like containers, hypervisors, cloud actually means. So with that, we can actually launch into this. Let's do a brief history of the cloud. If I define the cloud as a computer resource used remotely, I don't think too many people would actually disagree with that definition, but it's very, very broad. And because that definition is so broad, the beginning of the cloud actually goes back to this date, 1959, which is almost the very beginning of computers. The first cloud, which is basically a computer used remotely, is this. It's actually an IBM 709, and I should add for the IBM historians, I know the 709 predates 1959. That's not the point. The point is, in 1959, the world's first time-sharing operating system, so an operating system that could be used by multiple people simultaneously, was brought up on the 709. So before that, it was basically a batch job, so one job at a time, one person connected at a time. And with the time-sharing operating system, you could then use it simultaneously. So this effectively is a cloud. It's a remote computing resource. The remote lines were actually nice little RS-232 lines running, actually it was an IBM variant of RS-232 with EBDIC, but it was later standardized as RS-232, and multiple people could use it. So time sharing is a very different proposition from the virtualization we have today. The main problem with it is that there is no separation between any of the time-shared programs. They all have to be aware of each other, and they all have to take care not to step on each other, which if you think about it from the modern world of today is unheard of. That's a security nightmare waiting to happen. You just have access to everything everybody else is running on the computer. So this really wouldn't qualify for what we think of as modern virtualization, because modern virtualization is all about separating individual users into their own boxes, partly so they think they own the computer and you can charge them for it, which is very important in the cloud, and also partly so they can't break out of their box and do anything nasty to anybody else on the system. So in these heady days of computing, everybody just trusted everybody else and everything worked. But like I said, it allowed multiple users over an RS-232 network to actually function. And obviously, time sharing was soon replaced by task switching and virtual memory. This is the standard feature of almost all modern computers. It was what enabled Unix to come up. It was what enables all of the modern operating systems to come up. What it means is that you get effectively processors, and they each have a memory model where they think they own the entire memory in the machine. That's the virtual memory model. This technically is the first virtualization ever done. It wasn't, well, it was called virtual memory, but it wasn't really recognized as virtualization when hypervisors came along. But technically, task switching in virtual memory is the first form of virtualization. And it's sort of an odd kink in the journey, because if you think about it, we went from this task switching and virtualization to hardware virtualization, and then technically with containers, we went back to task switching and virtual memory again. And I'll get onto that in a bit as well. So the next most important thing in the evolution of the cloud is in 1962, the invention of the acoustically coupled modem. I don't think anybody in the room will remember one of these. There are people who, okay, you're even older than I am. You remember the acoustic coupled ones?
My father used to use them when I was a kid.
When I used the modem, they were actually directly plugged into the telephone network, but it took a long time for AT&T to be persuaded that it was safe to plug equipment that wasn't AT&T's into the telephone network. But the point is that RS-232 is just a cable. It extended from the computer to the teletype. So effectively, to use the computer, you had to be reasonably local to it, because RS-232 signals they transferred a long way. I actually have an RS-232 cable that's several hundred meters. Sorry about that. As you can see, I'm still somewhat active in the Linux kernel. But RS-232 effectively allowed the computer to be networked. And this is networking without what we think of as the modern internet. So you had to dial up the computer over the phone, and the computer had to have a modem to receive your incoming call. And it was all done at 300 bits per second, which is an unimaginably slow speed today. It was basically teletype, little terminals. You were just typing letters. And even as you typed the letters, you sort of, especially if it was a round-trip teletype, you could actually wait for the delay to see what you typed. But it did mean you could time share from home. So this, effectively, the time-sharing operating system and the modem was the evolution of what we think of as the modern cloud today, because now you could use a computer resource from anywhere, provided you had the correct equipment. The real revolution that actually leads to the modern cloud began in 1983 with a company called America Online. And again, 83 is actually after the birth of the internet, right? But America Online was actually a dial-up service. So it was, in 1983, it was actually completely disconnected from the internet. The internet was much more an academic and military thing. So all America Online did is they produced a large bank of modems that allowed many, many people to dial in. Their first offering was actually some sort of ASCII-type game where you had to download the application. But later, and later was about 3 or 4 years later, they added bulletin boards and email as the internet emerged. And then America Online themselves got their own internet connection, which allowed you to send email outside your America Online account. So with the dial-up, you were strictly restricted to communicating with your friends who also had dial-up with AOL. So this was the first service silo as well, largely because there was no one else to communicate until they were connected to the internet, and then you could actually send email from AOL into universities and your friends in the military and anybody else of the 10 or so internet users who existed at that time. But AOL is the first example of what I would call a traditional software as a service offering. It's software as a service because what you actually received from AOL, the first service, was a game. All you did was play this game. Playing the game, you didn't need to know anything about the back end. You didn't need to know that you were dialing over a modem, that it was online. You could play this game multiplayer, which was how the dial-up actually influenced it. But apart from the fact that you were communicating with someone else to play the game, you didn't need to know any of the details. America Online owned everything. So they owned all the way from banks of hundreds to thousands of modems to the actual computer system that ran it. All of the applications were written by America Online, and even the application they supplied to you to run on your personal computer was written by American Online. They owned soup to nuts absolutely everything. So this is what a traditional SaaS service is. If you own everything, you're a traditional SaaS service. It also provides a remote application. Modern software as a service is much different. Usually you don't actually have to own the platform. You can start with virtual infrastructure or something else. And usually you're providing a service. You may be or may not be providing an application. Once the World Wide Web started, they actually had a platform for applications. So this is the 1995, the emergence of the Mosaic browser from Urbana-Champaign. So now you actually can rely on people having a platform that's fairly uniform, even if they were on Windows or whatever the weird and wonderful Commodore 64, VIC, TRS-80, whatever. They usually had a web browser that actually worked. And it also worked on things like Sonos, Sparks, and so on. So now software as a service could be delivered as an endpoint to these web browsers, which actually is very convenient. And of course, today in the modern world, everything is internet connected. Nobody even bothers with modems and dial-ups anymore. Every device we possess is connected to the internet. So my phone, my computer, all have their own separate internet connections. And the point about this is that these connection points are multiplying exponentially. And so there is a vast, largely untapped market out there for providing services to all of these endpoints. And the more we grow the endpoints, as we extend into IoT and beyond, the greater and greater the need for these services, the more money there is to be made by somebody who's actually supplied them. So the object of the cloud as a remote computing resource is to enable cheap delivery of differentiated services to these endpoints. That is effectively what the cloud does. If you ever write software for the cloud or work in the cloud or work for a cloud service provider, enabling this is your job. It's not really anything else. And the problem with traditional SaaS, where you own everything from the modem banks to the computer hardware to the software that was written for it to the application that was run on the end, is it just does not scale for the vast diversity of this ecosystem that we're generating. So the AOL application, if you think about it, ran on PCs. If they wanted to target the phone, they'd have to rewrite their application. If they wanted to target IoT devices, they'd actually have to find a use for their application in IoT and so on. So the point is that if you start with all of the legacy stuff, you spend so much of your time maintaining the modem banks and the computers and everything that you actually have no time for differentiating at the top in the service, which is where all of the interest, all of the money, all of the people who connect to your service are to be found. So if you spend too much time on traditional SaaS, you can't actually scale to deliver what the modern world is requesting over the internet. So traditional SaaS is not a model that anybody, well, I'm going to make this statement that is completely untrue because I will demonstrate to you today that there is one traditional SaaS vendor who completely outstrips everybody else. But the idea is that what we want to do is to enable an ecosystem of differentiated developers to deliver these endpoint services, and we actually effectively segment what is going on. So somebody else is responsible for the sort of internet delivery, the connection point. Somebody else is responsible for the hardware. So we'd like somebody to be responsible for the operating system. The job of the sort of developer who services all the endpoints is really just to write the application. And so what we want to do is develop as big a pool of application developers as we possibly can to provide novel services to this ever-growing ecosystem. If we don't do this, the ecosystem will end up being useless. There's no point your fridge connecting to the internet if it can't talk to anything and do anything useful. If there's no application running on that fridge that does something with the internet, all it is a security threat within your house. It serves no useful purpose whatsoever. And I am not going to bring up an entire sort of cloud ecosystem from dropping computers in the desert to connecting the power and the cooling and everything, just so every time you take a Coke out of your fridge, I record that and send a message to your grocery shop saying, he's now taken 10 Cokes out of the fridge, he needs to refill. That is not a scalable business model. What is scalable is if I am a large cloud service provider like Google and I enable someone to write a tiny app that does that, and for a small fee, you can connect to it with your fridge and then it will do all of this. So the object is to enable this developer ecosystem. Amazingly enough, I think it was one of my arch nemesis from Microsoft a long time ago called Steve Ballmer who made this point. It's all about the developers, and it's still today all about the developers. And obviously, monetization of this requires a huge number of services. As the ecosystem expands enormously, to monetize it, we can actually cream off a smaller and smaller portion of what's going on. So the object is not to tax the service out of existence by charging too much for it. The object is to have as many users as you possibly can, charge them a small enough amount of money that they don't even notice it, and the service is useful, and then everybody in the ecosystem profits, from the person who's supplying the hardware, the internet, the application, and so on. So a long time ago, platform as a service was actually developed as a solution to this. It's become an unpopular term today, but the cloud provider effectively builds a platform to do this. And this makes the job of the application writer very easy because they just have to write to the platform. And obviously, there are many, many tenants. Each of these tenants can write differentiated applications. If they can write them really simply, this is the solution to our ecosystem explosion problem, because everything can just be written as this tiny application running on this platform. It sounds like nirvana. Everybody actually thought a long time ago this was the perfect answer to what's going on in the cloud today. Platform as a service. It provides a really efficient business model because once you can write for the platform, it's very easy to write lots of different applications as long as you understand the platform. The downside is balkanization. What I mean by balkanization is that applications have to be specifically written for this platform. This platform governs your language choice. So if you go to a Java platform as a service and you don't like Java because you want to write in Go, tough luck. You have to write in Java, otherwise you don't use the platform. This is where balkanization comes from, because if I have to have one platform for every language, now, there are only tens of programming languages, so it would only be tens of different clouds. But every programming language has all its own different quirks and its own different package managers and everything. And every cloud also has to supply all of these. So now, sort of, as the cloud makes choices for the developer, every choice it makes turns off a certain portion of developers because you don't have the package that they specifically wanted, even for their language runtime. So this is the balkanization problem with the cloud. It's balkanization problem with PaaS. Everything is prescribed. And it's actually a serious limitation that acts as a check on the ecosystem for two reasons. Firstly, because for every choice you make, you turn off a huge pool of developers. And secondly, because there are a lot of developers who have really quirky requirements for whom no PaaS satisfies, right? So we restrict our access to the developer pool, and as a cloud service provider, you restrict your profitability by restricting the number of people you can actually service. So this model, which looks so perfect because it's so easy to develop for, actually turns into an Achilles heel. This is why PaaS is not as popular today if you read the popular press, although I will actually say that one of the interesting things about PaaS, most of the clouds, doesn't require virtualization, traditional virtualization. So it often is not built on virtual infrastructure, often it's built on physical infrastructure. It does actually require you to be able to run the applications in separate boundaries, but these boundaries are often provided by the middleware. So in the Java PaaS cloud, the JVM was the thing that was actually providing the separation. There was no traditional container or hypervisor-based virtualization anywhere in that cloud. A lot of PaaS platforms do use more traditional forms of virtualization, but they don't have to. So this is one of the key things that I want you to take away. So it's often thought that virtualization and the cloud are one and the same thing. They're really tightly interlinked. This isn't really true. that the goals of virtualization and the goals of the cloud are very different. The cloud, if you get it right, is all about serving developers. Virtualization, if you get it right, is all about separating things and providing security primitives. They can be useful to each other, but only if you do it correctly. Although, now that I've said all of this, there is a PaaS platform today that dwarfs everything on the planet. Who knows what it is? It's still a platform as a service, still operating. It has more nodes installed than even Google or Amazon or any of the traditional cloud service providers. About, I think, 75% of the people in this room are using it at this moment. Nearly. It's Android. Android is a PaaS developer platform based for JavaScript. Every application is written in JavaScript. It's actually technically a reverse cloud because the devices sit in your pocket. They don't sit in a data center, but you still have something deployed on this device, this Android device that a reasonable number of you have. I gather universities are more Apple-centric. Apple is slightly less of a PaaS platform because Android specifically prescribes JavaScript. If you don't write your applications in JavaScript, you don't get them into the Android market, full stop. Apple is a bit more flexible, so it's not as much of a PaaS cloud. But this one is definitely the platform you have to write for if you want any application to run on the phone. And it can technically be a cloud because every time you download and run an application, it's talking back to home. If some nasty person, and this has been done many times, wants to upload a malicious application whose job is to mine bitcoins, and you all download it, they have a vast computer resource, a vast cloud computer resource to use for doing this Bitcoin mining. You'd actually be surprised to learn how many applications in the Android ecosystem do something like this. They surreptitiously tap the computer resources of your phone. So, Android is the biggest ecosystem. It dwarfs even Google and Amazon in terms of number of installed machines by far. Probably in terms of computing power, we'd probably say that the big servers are much more powerful than your phones. So it's probably not the top cloud in terms of power, but it is the top cloud in terms of devices. So, getting on to infrastructure as a service, which is the traditional thing you know about, this is what was actually successful. The reason PaaS wasn't successful is because it was too differentiated. People found too much difficulty, the developers found too much difficulty consuming it. So the next attempt was with infrastructure, which means all I really do is provide you with what looks like a bare metal machine, and I just leave it up to you to decide what you want to do with it. So this is where virtualization and the cloud really get to couple. Because without virtualization, I can't provide you with a virtual machine, I have to do it with a physical machine. And providing you with a physical machine in the cloud in the early days was actually a much more of a difficult proposition. It's sort of less of a difficult proposition now because of advances in virtualization that we can actually reuse inside physical machines, things like SRIOV. If you actually look at the recent Amazon virtual machine offering, if you run an inventory of your system, there is one component of that system that actually has serial numbers, and it turns out to be the memory DIMMs. So if you take the serial numbers of your memory DIMMs, reboot your virtual machine, and then take the serial numbers of your memory DIMMs again, you'll actually find out they've changed. And the reason is because Amazon is using SRIOV under the covers so that every time you take a physical machine down and bring it back up, they actually just give you a different piece of hardware. And they tune it on the fly, even in that reboot cycle. It's actually quite interesting. But the problem with all of this, virtual or physical infrastructure, is that the developer now gets to manage the operating system. So as a developer, your task is not just to build the application, you've got to manage the libraries and the language runtime and the operating system, and on a virtual machine, even the kernel. Any bug anywhere in that ecosystem is your fault, your problem, you have to sort it out. And this means that your expertise is now no longer just your little application, it's absolutely everything in an operating system ecosystem. It makes it very difficult for small shops, which is what we were trying to encourage, to build this sort of huge diverse ecosystem, to get into the business of building applications. If we have to do all of these stupid tasks that you don't care about for delivering your service and maintain the damn thing because there's a bug coming out, every few hours, it really makes life difficult for people. I mentioned physical infrastructure. So the job of the cloud service provider, number one job, of course, is this, to make money. That's what all cloud service providers are in it for. but they make money by enabling a huge and diverse range of developers to service this vast and growing market. And the point is, this market is growing exponentially and vastly. IoT is just one sort of side channel on this. There will be more and more and more internet-connected devices. And the more there are, the more differentiated services we actually need to bring up on these clouds to do that for them. And that means that we really do need to attract the niche developers, the people who can develop those strange applications that only serve, say your refrigerator or your toaster or your microwave and so on. And these people don't really want to be bothered with maintaining a whole operating system, right? They just want to give their application to the cloud service provider and collect the check every month from all of the users. That's all they really want to do. And to capture this sort of exponentially growing market is actually impossible for the cloud service provider. The only way you do it is by stimulating a developer ecosystem. There is no other model that is viable in the business. There's no other model that's scalable to all of these different things. And so the job of the cloud service provider, apart from make money, just boils down to remove all the developer issues. Any problem a developer has, it should be your problem as the cloud service provider. It should not be the developer's problem. The fewer problems they have bringing up applications, the more likely they are to choose your cloud. And in this world of trying to differentiate Amazon from Google, from the IBM cloud, from everything else, this should be the number one thing that you're concentrating on. So remove issues and provide useful primitives. Useful primitives means that I provide services within my cloud that application developers find useful when writing applications. Classic one is a database service, so they don't have to worry about persistent storage, but there are lots of others. But I do it in a non-prescriptive way, which means I don't constrain them to have to talk to my database service using Java or one of the weird connectors. They can just speak SQL if they like, or NoSQL if they like, so I just provide a range of services that they can connect to. However I do it under the back end, they don't care. And everything should just work for them in a language-neutral, developer-neutral way, so I can attract as many of these developers as possible. And now, virtualization. The key thing here is that an application developer does not want to care about virtualization. Virtualization may be what they run in, it's what they should not be aware of. The application developer is aware of virtualization, the cloud has failed. So the only people who should care about virtualization are the people running the cloud, because it's the bread and butter of how you run the cloud. If you make virtualization visible to the end user, it is a complete failure, because now they've got just one more thing they have to worry about. Instead of removing issues from the developer, you have added issues to the developer. So this means that as the world goes on and the number of cloud service people consolidate, the number of people in the world who actually care about virtualization is getting smaller and smaller, but the importance is not diminishing. If we're using it to run the clouds and the developers all develop on the clouds, we have to have a large range of people who understand how this virtualization thing works and can assist the cloud service provider doing it. It's sort of, I shouldn't probably say this, but it's the lesson IBM finally learned. It's the reason they're buying Red Hat. If you want to bring up a cloud, you have to intimately own, understand, service, and build the infrastructure itself, all the way from the hardware through the operating system on up, simply so that you can take the task of actually running the applications properly. You can actually take all the problems of running the applications to yourself and leave the developer just to code. Right? So there'll always be room in this world for people who understand things like virtualization and operating systems. It's just as the world moves on, fewer and fewer people will become aware of it. So your job as operating system people, virtualization people, hardware people, is to make yourselves invisible. Essential to the cloud, but invisible. Like I said, the cloud service provider does this by trying to be as responsible for as much of the stack as they possibly can. And as much of the stack includes the operating system, the libraries, and everything else. This is the current failure of the world today. Because if you take a closer look at virtualization, this is the standard hypervisor virtualization. So you have one kernel running across the entire machine, usually called the hypervisor. KVM, it would be a standard Linux kernel. It emulates virtual hardware, and on top of that virtual hardware, you bring up a new kernel and its system operating system. Problem with this is traditional IaaS. This whole thing here is the responsibility of the application developer. And this is the only thing they want to be an expert in. So you have it's like an iceberg. You have about 90% of the system that causes 90% of the problems that the developer does not want to know about. And with IaaS, you make them fully aware of this. And obviously, if we move to the wonderful world of Docker containers, now we only have one kernel, which is nice, but a Docker container looks like this. And it means that this is what you care about, but you still have bits of libraries and you still have bits of the operating system minus the kernel, and you have to build that whole thing into your Docker image. There's still 2/3 of this that you don't care about. So it's not quite an iceberg. We have got a bit better, but it's still, we haven't got to the point where your majority job is still developing applications. 2/3 of the stuff you still don't care about, and yet you still have to maintain. The ideal is actually this. This is an application container, a mythical application container. You'll hear Docker describe itself as an application container, but it's completely untrue. Docker looks like this. This is what PaaS did. So all those years ago, the rejected solution actually correctly did this application virtualization that is what we're still questing after today. So if you compare it, the reason people sort of like or dislike virtual machines, apart from all the maintenance problem, is these things are huge. They are really difficult to transport around the cloud. They're a maintenance nightmare because they have drift. There's all sorts of reasons why virtual machine images are nasty. Whereas container images are much smaller, they're immutable, they're much easier to handle, you can put them in a registry. Everything with container images really just works. And so one of the key attributes that enables containers to work the way they do today is this business of sharing. It's that single kernel that just does everything. The single kernel is actually both an asset and an Achilles heel to containers. The single kernel is why containers are so lean, mean, and efficient, and it's also why everybody thinks they have so many security problems. Containers are brilliant for scaling, and scaling is going to be a key to actually running the cloud. So if your service can't scale, as in, let's say I produce this application that checks the Cokes in your fridge and reorders them, and suddenly everybody likes that application, everybody has an internet-connected fridge, they all order it. So my customer base goes from 100 people kicking the tires tomorrow to 100 million people throughout the entire United States. Suddenly I have a scaling problem. Containers solve that scaling problem very well using Kubernetes and things. We can just replicate easily. Virtual machines, it's much harder actually to get the scaling right. It's not impossible, it's just much harder. If the cloud service provider is agile and clever like Amazon is, you can actually hide a lot of the details and get the scaling to work, but it's not as easy as with containers. And obviously, resource decisions made by the single kernel can actually be made much more efficiently. The biggest Achilles heel of a hypervisor is two kernels, because kernels each regard themselves as sovereign resource administrators. In a hypervisor, two-kernel system, the kernel on the bottom and the kernel on the top, they always fight over resources, because the job of Linux just runs in the cloud. The job of a Linux kernel is to take all of the resources and put them under its management. So as much memory as you give it, Linux will steal, for instance. So it becomes a very difficult job of the lower kernel to determine how much memory this instance should have to run efficiently. So all of these problems occur because it's very difficult to communicate information like memory consumption over a hardware abstraction, which is what a hypervisor is. So, boxing of applications led to this thing called the DevOps revolution. This is what Docker is most famous for, right? Everybody's heard of this, I presume. Docker is nothing more than an application packaging and transport system. It's a precise application and packaging and transport system. What it means is that the image I create on my laptop and run on my laptop will run exactly the same way on my laptop as it will on my test environment, as it will on the cloud. This is what we mean by precise transport. That's all it does. And if you believe Docker, this is what we use containers for. But the dirty secret is all that's required to do this is sort of immutability and layering of the file system, none of which is actually a property of fundamental container primitives in Linux. In theory, all of this can actually be brought up on a hypervisor, and there are various people like Clear Containers, Kata Containers, endeavoring to prove this is true. So none of the magic DevOps technology that Docker actually produced and said we're containers depends on containers themselves. And obviously DevOps today is all about the easy deployment of boxed applications, consistent environment and everything. But like I said, it's not container development, and it's not container dependent, and Docker is still infrastructure because it contains still in that image all of the operating system bits that you'd rather not worry about as the application developer. So Docker itself, even with DevOps, is not the complete answer to this problem of how do we enable the developer ecosystem. Because the application developer still needs to build and maintain the operating systems. Now, we have interesting words for it. The DevOps cycle includes, an entire sort of rotunda bit for maintaining the operating system. But if you're a small shop trying to build a novel application, you don't want to employ 3 operating system people who understand how to triage bugs and how to fix bugs and how to haul the images back and repair them when the operating system is discovered to be vulnerable. And realistically, for all application developers, about 95% of the vulnerabilities will be in the operating system, largely because the operating system is shared and a lot of people are looking at it. Fewer people are actually looking at your application. So chances are it has about the same amount of bugs, they just haven't been discovered. But the problem is, every time an operating system bug comes out and you're affected by it, you have to fix your Docker container to be not affected by it. Otherwise, you're going to find someone running a Bitcoin miner in your application, or stealing all your users' credit card data, or doing something else that you'll eventually get blamed for, and your application will be kicked out of all of these lucrative places for actually failing on. So unfortunately, you have to worry about maintenance. And DevOps tooling can reduce this burden, but it cannot eliminate it. And this phrase, it cannot eliminate it, is what would lead me to the conclusion that for all of the hype, and I say this quietly because I have a very fierce Israeli fellow back in Yorktown who is in charge of DevOps and would disagree vehemently, so she's probably going to be shooting me when I go back. But because it can't eliminate the problem, DevOps is not the solution to this developer ecosystem. So whatever the solution is, it's not DevOps. So for all of those of you who are working on DevOps, it might be time to think about, actually, would it make sense to work on something else? Because DevOps will never get far enough to solve this operating system problem. We can make it easier, we can automate all of the bits, but at the end of the day, the application developer who doesn't want to do this is still going to have to haul back and fix an operating system image for a bug they don't care about. And that is a failure in the cloud. And we need to fix that failure. So if we look at virtualization, because I promised you I would tie virtualization to the cloud, obviously we have the traditional virtualization. The red line actually represents the separation between the cloud service provider on the bottom and the user on the top. So the red line actually partly goes through your virtual machines because the cloud service provider is responsible for actually emulating the hardware. And the emulated hardware actually sits inside the virtual machine. You have no real access to play with this, but the cloud service provider owns this, but the red line is actually partially inside your image. And this, inside your virtual machine, this stack here is really all of the virtual machine image. And this dividing line here means that the kernel here communicates with the hypervisor using wholly hardware primitives. We try and mitigate, hardware primitives are actually very difficult to communicate information efficiently. This is why we get memory management fights. We try and make the communication more efficient with things called paravirtual drivers, but even paravirtual drivers can only go so far. The revolution they thought was actually going to make lightweight hypervisors more preferable to containers was this thing in Linux called DAX, which is almost equivalent to a paravirtual memory controller. So we thought that if we could actually solve the memory problem, which was the primary reason why the upper kernel and the lower kernel fight, we could actually make virtual machines orchestrate as efficiently as containers. The problem is that it turned out that the DAX primitives were not sufficiently paravirtual to communicate the information correctly. So they solved some of the problem, but not all of it. So even with Kata containers, we still get fights between the upper kernel and the lower kernel over memory management. These fights impact the density, and it means that Kata is just not as efficient to run in the cloud as a pure container. You contrast that with a container operating system. We've actually lifted the boundary from the hardware. Obviously, this would have been virtually emulated hardware. We've put it above sort of components of the operating system. Effectively, this red line is now occurring at the Linux syscall level. This is what operating system virtualization actually is. So by moving this line, what we've actually done is we've actually moved the way we communicate with the lower level. Now, to move this line is actually not as simple as I've made it sound. The container boundary depends very much on a hard system call interface. If that interface is not hard, containers don't work. And this happens to exist in Linux because of a complete accident. This accident is why Linux is now the operating system of the cloud, because no other operating system actually did this accidental thing. It turns out that Linus Torvalds, apart from all his rabid complaints and his squawking at everybody, really cared about backwards compatibility. He cared that I could take a binary written for the first Linux operating system in 1992 and run it on a modern Linux kernel today. So his requirement was that if you ever break this, this is where I jump down from the heavens from a great height and rip you to shreds. In the early days. Now, of course, he's been much more socially aware, and he's taken all of these, emotional awareness courses, and he rips you apart very gently instead of doing it with a flame-laden and expletive-laden email. But the point is,
what ruined Linux?
What's that?
Him being nice, what ruined Linux?
But he still cares about all of this. Even if he does it in a nice way, he'll still rip you to shreds. I mean, the net endpoint is still the same. He will not accept anything that breaks this backwards compatibility guarantee. This backwards compatibility guarantee are why containers work on Linux. If we didn't have that guarantee, containers would not work on Linux, because this is what gives the hardness to the system call interface that we require. Without this, I wouldn't be able to bring up, say, an Ubuntu container on the Novell kernel, because there'd be too much contamination of the interface. To give an example of an operating system that has this interface contamination, it's Windows. The reason Windows is struggling with containers is because of the fact that Windows interface between the kernel and user space is not as hard as it is in Linux. They have a soft boundary because there's a lot of cooperation between the user space and the kernel. And they did it for the best of reasons. It actually allows you to bring up the operating system more efficiently if part of your services live in the kernel, but conversely it makes it very hard to do containers on Windows. So when I was at Parallels, we actually did produce Windows containers. We tried to sell it to Microsoft. The downside is that in order to run a Windows 7 container, I actually have to run it on a Windows 7 kernel. And in order to run a Windows 10 container, I have to run it on Windows 10 kernel, and I can't mix them. With Linux, that is untrue. I can take any old kernel and run any old Linux container above it, and it doesn't matter. And it's this ability to run anything with the kernel that is actually what makes Linux the de facto operating system of the cloud, because it just makes the cloud service provider's life easier. It's not to say it cannot be done with Windows. It can be done. It's much harder. And would you prefer an easy job or a hard job when you talk to the CIO, which would make you more money? When you talk to the CEO, it's always the easy job that everybody wants. So the easiest route to the cloud is Linux, not Windows. That's why it exists today. As I said, the hypervisor interface sits at the hardware level. The container interface sits at the kernel system call level. So raising this interface from the hardware level to the syscall level actually meant that it solves a lot of the resource management issues because we only have one kernel. The one kernel sees everything, knows everything, manages everything correctly. There's no second kernel to fight with. This is the whole reason why container-based operating systems are so much leaner than hypervisor-based ones. Don't need to perform any of these stupid paravert tricks. Don't need to work out how to get a paravert memory description because the resource management is done by a single kernel. This is the great advantage. And obviously more efficiency of resources leads to density of orchestration. For a cloud service provider, this is very important because it governs the amount of hardware I need to buy to service all the developers. It means that you can do a lower tax per developer service, because if we're thinking of all of this as a tax-based ecosystem, the cloud service provider is taking a tax to exist. That tax might be you watching adverts if it's Google, but it's still taking the tax. And the developer is taking a tax so they can actually live and produce the applications. So this is sort of a tax-based ecosystem. And the more cheaply you can do it, the lower your taxes can be, as everybody in America knows. The other thing about this is that the container interface sits above the operating system kernel. So if you remember, I told you this iceberg thing where with a hypervisor image, you're responsible for about 90% of the stuff you don't care about, and for a container, you're responsible for about 60% of the stuff you don't care about. The 30% of the stuff you're missing is actually the operating system kernel. Because the interface moved, the application writer no longer has to find and fix bugs in the kernel. That becomes the job of the cloud service provider. So moving the interface actually moved some of the responsibility from the application writer to the cloud service provider. And if you remember my initial description of removing problems from the developer, this moving boundary of the virtualization actually did take some of those problems away from the developer. So it turns out to be a good thing both from the orchestration perspective from the cloud service provider, because they can bring it up more densely and either make more profit or tax you less. And it turns out to be a good thing from the application writer because you lost 30% of the stuff you don't care about. You still have the other 60% of the stuff you don't care about, but you lost the 30%. And like I said, it gives responsibility for kernel bugs to the applications, the cloud provider. And kernel bugs tend to be the things which come across most often. So usually there's a kernel CVE roughly every week. Probably in the libraries and everything, there's one roughly every couple of weeks. So it does reduce the amount of time you have to pull back and fix your images if you're a conscientious application service provider. And obviously, the developer is no longer responsible for patching the kernel. So this is one area of expertise you no longer have to employ in your development DevOps environment, which is all very useful. However, Docker and current containers still force you to own the rest of the operating system and find and fix bugs and all of that stuff you don't care about. So if moving the virtualization boundary improves the cloud, could we actually think about moving it again in order to make the cloud experience better? So I think with the remaining 15 minutes, we'll actually get onto the stuff that you might be interested in, because this might actually be a future research project. So if we moved the virtualization boundary again, would it actually help us with all of these problems? This is actually an interesting research topic that all of you might like to think about. Because if you think about platform as a service, the boundary was sitting here on the application, right? But it wasn't technically a virtualization boundary as I've illustrated in virtualization. It was actually a product of the middleware. And so it depended on having a specific middleware to actually work. So we can't get this boundary and reintroduce the platform as a service balkanization. We have to do this boundary in a much more generic way. So the question is, how would we do this boundary in a way that allowed me to have the generality of current Docker containers, so not get past balkanization, and yet still have the developer only responsible for actually writing the application? So what we're actually looking for, if we use the example of containers, is we're looking for a hard interface that sits at roughly that level, right? If we could find that, we might be able to move the container boundary up to that and actually put, well, they wouldn't be containers anymore, it would be something beyond containers. I suppose if you know Greek, it would be something like meta containers or what have you. But in Linux, we actually do have such an interface. It turns out that through another historical accident, a guy called Ulrich Streper, the glibc interface is actually almost as hard as the kernel system call interface. It's very backwards compatible. You can actually take a modern glibc library and take an app, as long as it's actually the correct binary. So we actually changed binary descriptions in Linux in around 1994, I think, from A out to ELF. But Linux kernel will actually still run old A out binaries. The glibc requires either A out or ELF, and I don't think anybody knows how to build glibc for A out anymore, so it pretty much requires ELF. But as long as you have an ELF binary the earliest ELF binary constructed in 95, 94 will still run on the modern glibc library. So this glibc interface actually has all the hardness properties, and so it's actually theoretically possible for us to consider that we might actually be able to move the virtualization boundary up into the C library and therefore move responsibility for everything C library and below to the cloud service provider. So provide a service that has much more of the responsibility of the cloud service provider. Because the orchestration is at this level, we're actually moving up to getting much more PaaS properties, many more PaaS properties for the cloud service provider. So it might actually provide an even more efficient way of orchestrating the cloud. And it might actually be possible because the boundary is hard enough. Nobody's actually looked at this or tried to do it, but it might actually be possible. There is still a problem. glibc is not high enough because the language runtimes all sit above glibc. So this is an advantage in that it still allows many different PaaS runtimes. So it solves the PaaS balkanization problem. But if the language runtime is sitting above glibc, that means that the application builder is still responsible for the language runtime, and they'd rather not be. So we're still going to need some sort of equivalent of the DevOps toolchain to try and take the responsibility of the language runtime away from the actual application developer. So we'd still need something like DevOps. We just hope that this shift would provide a sufficient transfer of responsibility and provide a much easier mechanism for the cloud service provider to take responsibility for the language runtime, such that we could effectively have what would be a pure PaaS platform without introducing any of the balkanization problems that PaaS today has. So without prescribing the runtime or doing anything else. So even in the worst case, if the application developer has to build a runtime into the image, at least they don't do the rest of the operating system. So perhaps we've eliminated another 30%. So you remember 30% went with the kernel, 30% might go with the libraries. So we have sort of the application and just a bit of language runtime. You're probably now sitting at 50-50 between what you care about and what you don't care about. But if we try and go the rest of the way and use DevOps to actually force the service provider to take on the runtimes, it may also be possible. In the DevOps tooling, there is actually a way of the service provider injecting stuff into the container. We were actually looking at it with a different project. And this injection into the container is what actually allows the service provider to even take responsibility for the language runtime. So it might actually be possible to use this scheme to bring up pure application containers for arbitrary runtimes on a standard cloud. And like I said, if we do this, we have to avoid the past balkanization. If you bring back the balkanization, the ecosystem will fail because the scaling is gone. And the scaling is what is required to get this ecosystem to function. And like I said, we need to supply language runtime and middleware, but we want the cloud service provider to be responsible for these. So we're going to have a new set of tooling. It may be very similar to our current DevOps. We'll probably take a lot of the stuff that we already have in DevOps. So DevOps isn't a throwaway thing. Hopefully there'll be a lot of learnings and a lot of tooling we can take from it. But whatever does this will be different from the modern DevOps that we have today. So with that, I think I've got 8 minutes left. So the conclusions, we'll leave 5 minutes of questions. The cloud is driven by the needs of the endpoints, not by the advances in virtualization. That doesn't mean that advances in virtualization can't be very useful to the needs of the endpoints, but the two are not as intertwined as people think. And obviously, when there is an intertwining, the cloud is very quick to take advantage of it, as it was with the container revolution. Although the thing it took advantage of in the container revolution was not the virtualization, it was the precise packaging and transport. DevOps is not the complete solution and never will be to the problem of making developers' lives simpler. So if you take on as your mission to make developers' lives simpler, DevOps is not the thing that eventually you will need. So we should be thinking about new things and new paradigms. And as researchers, that's your job. And the opportunity is growing for another paradigm shift in virtualization. If you believe Docker, the paradigm shift from virtual machines to containers, it was this huge wave that engulfed the ecosystem. For a while, nobody would even touch your cloud if you were talking about virtual machines. We're sort of teetering backwards on that. So people have discovered that containers aren't quite the sort of thing they wanted. And some people are now bringing back sort of traditional virtualizations. But from about 2014 to 2016, there was this massive wave that basically just drowned hypervisors. So they were sort of stuck at the bottom gasping. They're just about coming up for air again. But if you want to be really famous, find another virtualization that can do this wave again. You'll at least be famous for 2 years as Docker was. So that fame will be enduring. It's much more long-lasting than just writing papers, even for Nature. It's something people remember in history. And moving the virtualization boundary might be how you get this to happen. So opportunities exist today for all of you that go beyond sort of what is currently exists today to make a pathway to the future where actually everybody pays attention to what you've done because suddenly the industry is all excited by it. So the technological pathways exist to go beyond the current containers, and we should actually be researching whether we can produce anything useful from it or not. As far as I can tell, there is almost no research going on in academia today towards this. There's only a few people in sort of institutions like IBM, Google, probably Amazon thinking about this problem. So we need many more people actually thinking about this problem if we're to find the solution. Remember, Docker did not invent containers. They just took advantage of them. Containers was invented 10 years before Docker appeared on the scene. In fact, it was nearly 15 years before. So for 15 years, people have known about containers but hadn't known how to exploit them. So there was a lot of work and sort of finally finding the right opportunity that had to be done to make this revolution happen. So just researching primitives isn't enough. You're going to have to figure out how people use them as well. This will be very important. But, like I say, you could potentially start a new post-container or meta-container revolution. Wouldn't that be fun? And if you enjoyed this presentation, it was written in Impress.js, which makes me a web developer, because it's all HTML primitives. And with that, I'll say thank you, and I believe we have 5 minutes left for questions, so thank you. Okay, Ashvin, you choose the people.
All right, I get to choose. We'll start with you.
You equated the developer's problem with application container, but actually application is lots of containers. So it seems the developer's complexity is shifted. They have to load Kubernetes dialect and things like that to actually run something perfectly, and that's not their job either. So it seems like there's another level of complexity here that you didn't address.
So I believe the question boils down to why didn't I diss microservices? The answer is because I don't have enough time. So the point that was made was that our current modern incarnation of Kubernetes doesn't concentrate on somebody who's building a single application, a single thing. We talk about these things called microservices, which are lots of mutually collaborating applications. And in fact, microservices are building complexity into the ecosystem that developers just don't want. And I would absolutely agree. I've never been convinced that microservices are the right answer for this, because they build complexity at the level where the application developer can understand, but if it's complexity you can do without, why bother with it? So I would agree with the premise of your question. Next question.
So it seems like what you've really generalized here is this notion of a hard interface, something that's backwards compatible, which traditionally was x86 hardware, but now Linux kernel or glibc and so on. Is there a reason why we don't just say, look, a container is hard interfaces all the way down as far as you want to go, and we'll provide the top one and make sure it doesn't change? Is that and allow it to be a different level? So you get a little bit of balkanization. But if someone says, look, I'm happy with glibc, you give them that interface. Well, I don't want glibc, I want to substitute muscle, but I do want to still have, let's say, the kernel interface. Or someone else says, I want to try a new kernel. Is there a reason we can't provide all of those simultaneously and in a way that says, pick the one that's as high up as you want, but allow people to experiment on the other side?
Well, so the reason is, as you stated it, the higher up we go, the worse the balkanization becomes. So I don't think you disagree with my contention with balkanization is what killed PaaS. So we know that going too far up in the balkanization realm leads to the death of whatever you're trying to build. The question you're asking is, can we go a little of the way up, gain some of the advantages and yet still not die? The answer to that question is, I honestly don't know. There isn't enough data out in the ecosystem for me to make even an educated guess. If I were to guess reasonably, I would say that sort of balkanization seems to be slightly exponential in terms of the way you go up the stack. So even just going up the stack a small way into the language runtime seems to introduce quite a lot of balkanization, seems to make your cloud quite a lot more difficult. So as a betting man, since I have this research budget I have to actually invest, if you want to know where I would make the investment, I would make it at the interface that isn't balkanized, because I know balkanization was a failure and I'd be afraid to recreate that failure. The question of whether it can be done or not, I really don't know. I wouldn't invest in that, but I think you might be right. I think it might not be impossible to go a little of the way into the balkanization.
But what I'm suggesting is a little different. In other words, if you have several hard layers, machine code, operating system kernel, library, and then maybe even sort of basic glibc and then set of libraries, you could say, look, these are 4 hard layers, right? 4 hard interfaces, and I'm going to guarantee backwards compatibility with each one. So normally you're going to choose the top one because, as you said, it's the easiest.
Yes.
But someone else says, well, but I need to choose this one.
But the language...
Right? Then you have a little balkanization, but you still are supporting it on this side, so it's not so bad.
So the question I believe you're asking is, can we do it with do it by making all of the libraries part of the boundary, right, and still having the language runtime above that?
Yes.
The answer is, Theoretically, yes, but in practice, if you look at the interfaces, I mean, think of OpenSSL.
Yeah.
What happened when we went from OpenSSL 1.02 to 1.1?
Right.
Everything broke.
Right.
So unfortunately, there are a lot of libraries out there that do not obey this hardness property.
Okay.
And that is going to, so when I look at the libraries that I can find that do, the only one that really seems to satisfy this, will you run a binary from 95 on a 2019 library? It's glibc. Nothing above that seems to have that property, largely because everybody else really wasn't concentrating on this when they were writing their libraries. They got it wrong, and they do things like OpenSSL, which involves, we'll just completely rewrite it, break all the developers, they won't care, they'll just learn to do it, and that completely destroys any interface hardness. So that's why I would still make my bet at the glibc level, but I'm not saying you're wrong. I'm just saying, on probability, I think I'm doing it this way correctly.
One more question.
What's your opinion about things such as Amazon Lambda, Google Function, things that are said to be like the next step after the container?
Well, so the question is about functions and Lambda, which are effectively a scripting environment for the cloud. They call it event-driven, and it's a scripting environment that's designed to take event inputs and trigger outputs, but it's effectively a scripting environment. So scripting environments are interesting in that people don't tend to regard them as balkanized as PaaS, because scripts are much more general and much more simple, and they can call out to a lot of other things. So I would have to confess, if you were to actually ask me what my favorite language for the cloud is, I'd say PHP. PHP is also a scripting language. It's not really a prescriptive runtime language like Node or Go or Python or anything else. So I think there's definitely a place in the cloud for scripting languages. But scripting languages don't work sufficiently well to build all of the diversity of the ecosystem that we have to build in order to service all of the endpoints. So I think scripting languages like Lambda, functions, whatever, OpenWhisk will be part of the solution. But again, I don't think they'll be the whole solution. Right? And what we have to do is, it's not enough just to build a partial solution. Partial solution balkanization is what killed PaaS. We don't want to go down that road. Whatever solution we build has to be complete. And it can contain components like that, but I think I wouldn't agree with anybody who says that is the answer, because I don't think it is.
All right. We're out of time. We'll talk right after. So can we thank the speaker now?
Thank you very much.